now let's go over 16.1, which is on line integrals. So go ahead and write down this definition. So first, we'll talk about a curve and it being smooth. So you've seen this definition defined using the rectangular function, and that it's smooth for normal situation we've looked at in the past. You don't have to write this down, but if you have y equals f of x, then it's smooth if basically f prime exists and continuous. So in this case, when you have it a function defined in terms of r of t, we say that r of t equal to this, right? So that's like a spiral or something, is smooth if each of these derivatives, and it's not a partial, each of these derivatives are continuous, just like this one, on AB, and not simultaneously zero on AB. That's the only other stipulation that we have. And then we look into what's called piecewise smooth, which is really what most of these theorems are defined on. And a curve C is piecewise smooth if that interval, so if you have some interval down here, is partitioned or can be partitioned so that it's smooth on each of those partition. And it's a finite number of subintervals. So I'll show you an idea what the graph might look like. Oops, do it like that, okay. So you maybe go like this, it's smooth, but then here it has a corner, and then another corner like that. Then here and here it's not smooth, but it's still a finite number of subintervals. And then your R of t is being traced out like this, right? So that's your R of t. That's tracing out that function, that vector valued function on some subinterval. And that can be in the xy plane or in 3D as well. Okay, now line integral. So that's just a smooth curve using a vector valued function. So line integral looks like this. Oops, why'd I do that? So a line integral, you say integral over C, the curve, it's of f of x, y, z ds, which we'll define, is equal to the limit as the norm of the partition, which is normal, approaches 0 of the sum over all of the i's. That's how they define it. Of f of x sub I, y sub I, z sub I, delta s sub I. And so what you're doing is you're taking some curve and you're adding up each of these little ds's, these little subintervals. That's your delta s, the length of that. So your delta s is that length, but it could be arced like that. So it could be curved. So that's your delta s sub I. Now how to calculate that, we will define that. Okay, then your ds, this is kind of, so anytime you see ds, you're not going to know how, you use the formula, but that's meaningless to us. Like we have to figure out the formula is based off of what's given and your R of t, like how your R of t is defined, like here. So here's your R of t, how is that defined? So ds is equal to the magnitude of, so remember how we know ds is here, it exists because it's defined over c, and c is defined by that. Okay, so that's where it's coming from. So ds is the norm of the r prime of t, which basically comes out in the derivation, dt. So that's equal to the square root of the sum of the squares of the derivatives, dt. So that's basically x prime of t squared plus y prime of t squared plus z prime of t squared. And so we've done that before in the past, or maybe you have seen that before in the past. And that comes out when you use the mean value theorem and you get that derivative in there when that curve is being defined, when you're basically finding the length of the curve. So if you basically, if you take this out right here, then that's the length of the curve, which we have looked at. And then I guess I write that down. So let's write that down, have it more solid. If f of x, y, z is equal to 1, then the integral of 1 ds is equal to the integral from a to b of the magnitude of r prime of t dt. And that, of course, is the length of c on a to b, wherever that is. Okay, so now we look at ways to evaluate the line integral. So we're going to call these evaluation formulas. So these are evaluation formulas. So we have the line integral over c of f of x, y, z ds equal to the integral from a to b. So it's f of x of t, y of t, z of t, because that's how x, y, and z are defined in terms of t, and then times the square root of those primes, the same as above, dt. So that part is the same as this. So that's x prime of t squared plus y prime of t squared plus z prime of t squared. And it helps to remember that this is your r prime, magnitude of r prime dt. Okay, so that is your ds. That's what we need to remember that. We need to remember your ds is this. Oops, I just put ds in there. This should be dt. That's dt. Okay, so that's what it should be. So this is those match. It helps you remember. So when you see ds, you need to always convert that to something you can actually evaluate. So let's look at an example of that. So evaluate the line integral over c of 2x squared y ds, where c is the portion of the parabola y equal to x squared from -1, 1 to 2, 2, 4. That's your P. So this is given this to you in rectangular, which we didn't really do above. We need to convert this to a form we can evaluate. So let's go ahead and draw in our parabola. So if they give you a parabola or something you can draw, you always want to sketch it. So our parabola is going from -1, 1 to 2, 4, which makes sense. So 1, 2, 1, 2, 3, 4. So it's this little piece of the parabola here, like that. So there's your -1, 2. Here's your ordered pair 2, 4, -1, 1. So that's your curve. So we have f of x equal to x squared. What we want to do next is define the curve parametrically. And that's never difficult. Well, I wouldn't say never difficult, but it's easy to do if it's in rectangular because you just let x be t and then you just evaluate for y. So define the curve parametrically. So if it's an explicit function, it's pretty easy to do. So let x equal t, then your y is t squared. And that's for the same interval that we were talking about from -1 to 2. So then substitute for x and y in terms, that's two words, but in terms of t. I just put that together too closely. So we have, that I can't live with. Okay, so we have that f of xy, then, that's your given function in the inside. We want to convert that. So that's 2, right, like above. 2x squared y is equal to 2t squared t squared, which is 2t to the 4th. And then your ds will be the square root of, now this is x of t and this is y of t, so you do those derivatives and take their square. So it's just 1 squared plus 2t squared dt. Now we substitute that, so you have to calculate your ds all the time. You got to figure out what that is. Now we take this and plug it back into here and do that substitution. So, and I'll recopy, just make it look nice. Integral over c of 2x squared y ds is equal to the integral. Now we just go from what t does. T goes from -1 to 2, so those are your limits. -1 to 2 of 2t to the 4th ds, which is the square root of 1 plus 4t squared dt. All right, and so that's your ds. You always have to calculate and figure out. Okay, so this is where I need you to go. So to evaluate this, there's going to be different methods to do that. I have an approximation. That's all I ended up doing. So that's the approximation you can get. You can double check that. It's 45.391. So I don't want to spend too much time or a bunch of time going over this one of how you might do that in exact form. I just had this happen to have the approximate form. So what you can relate these to or think about these is different. This is just an evaluation, this question. But if you have like a wire with varying density, I don't know why you'd have that, but suppose you did. And then you are looking at the distance that you have, some of your delta S, but the density is different here versus out here. Again, not sure how that would be the case, but that would be a line integral over the C, and then you have your density function, x, y, z here, ds, and that'll give you mass of the wire. So that's another way to interpret this. So that's just another example I wanted to go over. So mass, and that's what they do in the book too, of a wire could look like that. So the mass is the line integral. So it's like the distance, but then your density function is increments on the line. So delta x, y, z, ds. And then their delta x, y, z is density per unit length. That's what it would have to be. So it's per length is the density. Okay, so just another example. Other examples for line integrals, make sure you evaluate those and look at those. But we want to get into the next important theorems, which is in 16.2, and different forms of these calculations. Okay, moving on.